Let's continue our discussions on design principles. We looked at a few design principles already, but the most recent one we looked at is the open-closed principle. Open-closed principle is one of the most vital principles. I've used it several times over and over, and it really has a huge impact on extensibility. But the next principle we're going to look at is going to be a principle that has a very big impact on use of inheritance, or I should say proper use of inheritance. Well, unfortunately, inheritance is one of the most abused or misused concepts in object-oriented programming. We can go ahead and inherit from a class, but then the burden really starts. When you are trying to use a particular object, you simply become the user of this object and you can simply delegate your request to that particular object. But however, when you're trying to inherit from a class, you are required to fulfill a certain contract. We talked about design by contract versus design by capability in another presentation. We also talked about inheritance versus delegation. Well, this really brings together a lot of these ideas together in terms of learning this through application of principle, and I think this is a brilliant principle. And this principle is called the Liskov substitution principle. Liskov substitution principle directly head-on attacks about inheritance and how we actually use inheritance. So inheritance is often used to realize and reuse an abstraction. For example, we use inheritance to define a is a or kind of relationship. A car is a vehicle, a woman is a human, a dog is an animal, and we keep bringing up all of these different kinds of hierarchies we normally provide in our modeling. Now, we of course also use polymorphism to attain extensibility. But unfortunately, in a lot of statically typed languages, the inheritance becomes a gateway to realize polymorphism, which is really unfortunate, but because of the type checking constraints, normally we can't really make use of polymorphism as easily without inheritance. But unfortunately, like I mentioned, inheritance is one of the most abused or misused concepts in object-oriented programming. When we inherit from a class, we have to take care of a certain contract to fulfill. And that's exactly what the Liskov substitution principle is underlining. So what does it really mean to measure a quality of inheritance? How do we really do this? So Liskov substitution principle says functions that use pointers or references. Well, in C++ we use pointers, in Java and C#, in a lot of other languages we use references. We can treat pointers and references as interchangeable for this discussion. So when a function is using a pointer or a reference to an object of a base class, it must be able to access that object through that reference or pointer without knowing whether the object that it's referring to is an object of base or one of the derived classes. So Liskov substitution principle says functions that use pointers or references to a base class must be able to use the objects of the derived class without knowing that it's actually using an object of a derived class. Now, this may not be very obvious when we look at it. It's like, good, that's exactly how we use it. So what's the big deal? Why should we talk about it? Well, unfortunately, though, that's not what happens a lot of different times when we violate the contract of inheritance. What is the contract of inheritance? That's the next question. After all, we are overriding methods. We are making sure the signature is correct. The method names are correct. What gives? What should I do more? Well, there is a very implicit or underlying contract and conditions associated with a particular class, and we have to really consider that very deeply. And if we don't consider that, it becomes quite problematic when it comes to doing design. And I'm going to talk about this in concepts first of all, and then we're going to look at least 2 or 3 different examples, and we will look at good examples where Liskov substitution principle is held up, and we'll also look at examples where we fail at Liskov substitution principle as well. So that gives us a nice idea about a good usage and compliance, and it also gives us a good idea about where and when we could potentially be violating this. So Liskov substitution principle is one of the most fundamental principles we should think about when it comes to inheritance. So when you say a class B inherits from a class A, it usually means is or kind of. Well, the word public here simply means that it's a public inheritance in C++. Java and C# only provide public inheritance. There is no protected or private inheritance in these languages. But language like C++ provided that kind of capability. So ignoring public for a minute, we're just talking about a regular inheritance as we know in languages like Java and C#. What does it mean for a class B to inherit from a class A or a derived class to be inheriting from a base class? Well, the very first thing is that B is a kind of A. So it means that if you say dog is an animal, dog is a kind of animal. If you say man is a human and woman is a human, then men and women are kind of human. So it's a is a, or man is a human, woman is a human. It also means that everywhere an object of A can be used, then an object of A can be used as well. Let me restate that, I'm sorry. Anywhere an object of A can be used, an object of B can be used as well. So in other words, if you say humans are welcome, then both men and women are welcome. But of course, we have men's room and women's room, and of course, we know where to go and where not to go, and this is an example where it's restricted to that specific type. On the other hand, if we have a particular event where everybody is welcome, then clearly both men and women can go, absolutely. On the other hand, if there is a certain event where only women are welcome, so certainly you don't want to show up as a man, but absolutely can show up if they are a woman. So in other words, if the base class is accepted, then any of the derived class instances can be passed to that particular function. So let's look at what this really means in an example. Suppose I were to have a class called, let's say class called human, and then I have a class, let's say class called women, and women extends from human in this case, and then I of course also have a class called man which extends from human as well. And if I were to write a function, a method, and I'm going to say in this case public static, let's say, and this is going to say visit, and who can visit? Let's say a man can visit, so I'm going to say a person. Well, in this case, of course, you can only send an object of man. You cannot send, or you're not expected to send, an object of women to this function. However, if I change it to a human, for example, then what I could do is I could call the visit method. I could send a new woman object to this, and I should be able to send a new, and in this case, man object to it. Now again, you may question and say, that's exactly how every language works, right? So why talk about it? The principle actually is about the fact that you must be able to send either one of those objects, and neither one of them should be rejected, not just at compile time, but also at runtime. So that is the emphasis in this particular case, is that they either one of them or any of these objects could be passed in. What's true of an object of A is also true of an object of B. So what this means is, if something is true of a human, that is absolutely true of women and of men as well. So in this case, what it really means is, if human can speak, then men and women can speak. If human can sing, men and women can sing. You cannot say, well, there's something that a human can do, but either one of them couldn't do. And that's one of the reasons we could say there are certain qualities that are not really a part of a human, but they are part of either a woman or a man. And the reason for that distinction is they're not common as a human. But on the other hand, sleeping, right? We all sleep as human beings, and so do women and so do men. Some less than the others, but on the other hand, we all tend to sleep. On the other hand, there are qualities that you could expect of a man, for example. Well, and for example, having a beard, which is optional, having a mustache, which is optional, but generally, of course, we expect that this is the growth of men to have beard and mustache, and so you couldn't say humans have beards and mustache. So, likewise, there are qualities you could define for a woman and say that's expected of a woman. And again, there are optional qualities, but that doesn't mean every one of them is required. But clearly, that's not available in a human to provide. Similarly, we could say there's a class called animal. Now, we could say that all the animals have an animal instinct. Well, that means every single animal is required to have that animal instinct. We cannot say, well, this is only to this group of animal, but I'm going to raise it to the base class. Well, we can't do that because there are certain types that wouldn't have that quality. So this principle simply, this particular thing says that what is true of a base is true of every single object of the derived. So what is at the top is so general, it's applicable to every single instance. And A represents a more general concept than B, and so in this case it says a human is more general than a woman or a man. On the other hand, we can also argue in reverse, or as a corollary, that B is a representation of a more specialized concepts than A, and obviously a man is a more specialized human, and woman is definitely a very specialized human as well. And so there are characteristics that a man has that a human doesn't, and there's a characteristics that women have that a human doesn't. And so there are specializations from that. So in other words, everything that's true of the base is true of the derived, but not necessarily the other way around. But where it gets very tricky is anywhere an object of A can be used, an object of B can also be used. And so as a result, in this particular example, if we say human are welcome for this visit, then any object of man or woman can be sent without any particular object being rejected, and that is essentially what this is all about. But how do we make sure this actually works? Just because the compiler says this is okay, it doesn't mean it's okay. It should actually work in reality at runtime. So this brings us to what's called an advertised behavior of an object. Now, we talked about design by contract versus design by capability. This is not just contract as defined by the interface of the class by looking at the method signature and say, oh, you're receiving an integer and a double, so I'll make sure I'm keeping an integer and double. That's not what we're talking about here. It is that plus not just the letter, but the intention of the interfaces. So an advertised behavior. So what are you implying by writing this particular code? And that is what this is really stemming on. So advertised behavior of an object consists of two things. There's preconditions and there are post conditions. A precondition is what we expect before we call a method. A post condition is what we expect after we execute successfully that method. For example, you could tell me, Venkat, sit down. We could argue a precondition for me to sit down is that maybe I am either standing or I'm laying down. So I cannot be in the sitting position already if you want me to sit. Likewise, so the precondition for sit down, we could argue is either I'm standing or I am laying down. But if you want me to run, then the precondition probably should be that I'm already in a standing position, assuming that I'm a robot and I need to be told every single instruction separately. So if I'm laying down and say run, well, that's not going to work. I got to change a few other states before I can run. So a precondition for run is maybe I should be standing and not sitting or laying down. But what is the post condition for sit down? If the precondition was met, and everything else was satisfied, then the post condition of sit down is I'm in a sitting position. On the other hand, the post condition for run, assuming that all the preconditions were met and the function was successful, would be that I'm running. So in a sense, we could talk about what is expected before and what is expected after. It could also be a bearing on the parameters you send and the results you expect. So we want to think about a advertised behavior of a particular class. So if I were to, let's say for a minute, consider a class called, let's say class called random. So this class random says, I will give you, let's say public int, it says next to rand, and it is going to provide some implementation, let's say. Now, one of the things we could expect of this particular class is it's going to return an integer. But the class may prescribe to say it only is going to return positive numbers. Now, even though int could be negative or positive, the documentation of this particular function or all the unit tests written for this function with the intention tells us that this will only return a positive number. It may also give us a range, for example. So we could say, for example, int from and int to. And this may be an inclusive range. So it may say, I'll start from, I'll end to, and I'll give you a random number only in this range. So what is the advertised behavior for this particular random class if this is the only method we have in this particular random class? We could even turn this into an interface, if you will, rather than keeping this as a class for now. So let's say this is an interface. Now, what is the advertised behavior of this random interface? The advertised behavior is there is a precondition and a postcondition, and the precondition is that we are giving a from and a to, and we could say the from should be 0 or more. So we could write down, so we could say from is greater than or equal to 0. We could also say to is greater than or equal to 0. Well, not so fast. We could say that to is greater than or equal to from. So the random next rand may insist that for us to be satisfying the precondition, we need to always give a from which is 0 or more and a to which is greater than or equal to from, for example. Now it also, so that is the requirement that we are expecting, precondition. Now because the rand doesn't have any state, it's an interface, so there's nothing to really tell. But what is the post condition? The post condition in this case could be the return value is less than, so we could say from is going to be greater than or equal to the return value which is less than or equal to 2. So the random may guarantee a post condition that it will be in this range of values from and then return value and then 2. So if this is the interface we wrote and our class says I will conform to this. Now if I come along and I write a class called randomizer, and then let's say it is going to implement the random function. Now I'm interested in implementing this function called nextRandom. So let's go ahead and say implementing the nextRandom. Now what am I going to do? If I were to return a from here, I am not in violation of the requirements, but of course I need to make sure that the preconditions are met. So what I could potentially do as an example is, I could say if from is less than 0 or if rand 2 is greater than, less than from, then we could say throw, for instance, and I could say throw new runtime exception, and in this case the exception is going to be from should be greater than or equal to 0 and we could say to greater than or equal to from. So we could throw an exception. And then of course we could return whatever result we want to return from here. Maybe one other condition, post condition that says here is that the result result will be in a random distribution. So we could say random distribution. So what that means is every time you call, it might be over a distribution of values, and we could talk more about how the distribution happens and stuff like that. That could be potentially the way to specify this particular condition. So now that we talked about the pre and post condition, what does that really mean? Well, in design by contract, we have to ensure that the advertised behavior of the derived class requires no more and promises no less than the corresponding services of the base class. Well, that's a mouthful, Let's tear it apart a little bit and understand what that really means. It means the derived class services, methods of the derived class, things that they provide for us. So the derived class services should require no more. So imagine for a minute, if I require let's say I'm teaching a class where I require that everybody comes to the class with a computer. Now tomorrow, maybe I couldn't become sick, I couldn't show up. A substitute comes over, and if a substitute says, oh, I will only teach if everybody in the class has one particular type of machine. I'm sorry, that substitute is of no use because a substitute requires more than I did. I said any computer is allowed in the class. My substitute says, oh no, I'm not going to let you do that. I'm going to require one particular type of computer while my substitute requires more than I do. So that's not allowed because then it's not substitutable. Likewise, the services that you have in the derived should promise no less than the services of the base class. If I promise that I will teach you a good design ideas, and if I cough and a substitute show up, and the substitute says, oh, forget about design, who cares? I'm going to teach you playing golf. Well, sorry, as fun as that may be, better than doing design, I hope not. That's not good enough. But if my substitute says, I'll teach you design, and I will also teach you better coding practice, and I will make you an expert in a particular area in the field, well, merit to the substitute. You would rather have the substitute teach the course because substitute delivers more than I am promising to deliver. But the substitute can never do less than what I promised to deliver. In a similar way, if you consider this particular class, if I am going to come back here and say class, let's call it as a efficient randomizer. Let's go ahead and say efficient randomizer. Now this efficient randomizer says extends a randomizer, and I want to implement, of course, this method called next to rand. But in the implementation of the method next to rand, and I'm going to just leave it over here, we can implement, let's just say return from for a minute. But I'm going to suggest a few things. The very first suggestion here is this efficient randomizer says that from should be, let's say it tells us that to that you provide should be, and it says should be to at least 2 times greater than, let's say greater than from. So my efficient randomizer is super fast, better way to efficiently produce random numbers. But the efficient randomizer says, aha, but I got a problem. For me to provide such an efficient algorithm, I can only support the case where I would expect that the 2 that you provide is at least 2 times greater than from. We are violating Liskov substitution principle. The reason why we say we are violating Liskov substitution principle, notice the code would not give us any error. The compiler will not give us any error. Why? Because the base requires an int and an int, and the derived is receiving an int and an int. The compiler wouldn't complain. And it's returning an int and returning an int, so the compiler wouldn't complain. But we are saying, well, in this code, I'm going to now rewrite it as if the 2 is less than 2 times from, and then of course I could do other checks. Then I'm going to say throw, and I'll say throw in this case new runtime exception from blah blah blah, and finally 2 should be greater than or equal to 2 times from. Now notice my requirements are greater than the requirements, more than the requirements of the base class. In other words, I am more strict as an efficient randomizer compared to this randomizer. And so as a result, this randomizer is not substitutable anywhere a randomizer is being used. So if my code is using a randomizer, my code can no longer use a randomizer now. And why? Because this is going to violate the expectations we have on this particular code. So we got to be very careful in how we design this. In fact, let's see why this is a problem with a little bit of an example here. So let's go ahead and just have the randomizer. So let's say we have a randomizer that we have defined. And what does the randomizer do? Our randomizer says, I will give you a method called next to rand. And this next to rand, simply at this time, all it says is, from is if greater than or equal to 0, and to is greater than or equal to 0. So from should be greater than or equal to 0, and to should be greater than or equal to from. So now I'm going to say randomizer, and I'm going to say randomizer equals new randomizer. I created one, and I'm going to say use, and I'm going to send the randomizer to our wonderful function. So now in our code, I'm going to say in this case, I'm going to use randomizer. So this is going to take a randomizer, and our randomizer says, hey, what do I want to do? And our randomizer says output randomizer dot, and it's going to say next to rand, and it's going to send in, let's say, a value in this case of, oh, let's say 2. And it's going to send a value of, let's say, about a 4. Now, the question really in this case is, do I need to worry about exceptions? Well, the answer is no, we don't worry about exceptions. And the reason we don't have to worry about expressions, worry about the exception is, the contract specified here is that from is greater than or equal to 0, and it is that we're sending in, and to is greater than or equal to from, and it is. So we're not violating any behavior that is expected or precondition that's expected, so we are good. So let's go ahead and fix this little thing. So randomizer, let's see if he's happy with that. So he's still complaining that he's not happy with the word. Let's actually ask him what he's complaining about. Just curious. So in the word, it's unhappy that it doesn't like the word, but it doesn't tell me, oh, there it is. Spell checker inspects helps locate typos and misspelling, and he's not happy with the spelling of this. Well, all right. So I'm going to leave that alone for now. So that's my randomizer. Now what am I doing here? When I run this code, sure enough, it gave us a value of 2. And okay, that's the value we received from it. All right. But what if I now come here and I'm going to go ahead and create a class called efficient, let's say, efficient randomizer. So once I create a randomizer which is efficient and that extends from the randomizer, and very quietly I'm going to say override the next rand. But in this code, what I'm going to do is simply say if the from is less than 0 or 2 is less than 2 times from, I'm going to now say throw, and in this case new runtime exception, and I'm going to say from should be, let's say should be, and this is going to be greater than or equal to 0, and 2 is greater than or equal to 2 times from. And if it is, I'm going to do some work here. Whatever work I want to do, provide this wonderful, beautiful, really fast, randomizer, and eventually it returns, let's say, some value. We'll just fake it here with from plus 1. Well, now what's going to happen? Now, if I were to run this little code, what is going to happen if I use a randomizer here, and it still produces a result of 2? But on the other hand, in this case, if I were to send, let's say, not a randomizer, but efficient randomizer, and we'll call it as efficient randomizer equals new efficient randomizer, and I send a efficient randomizer, what's going to happen? Well, not a whole lot. It still works. But we are in violation of Liskov substitution principle, and we may not even know that for a while. But imagine we have another situation where a user comes along and says, I'm going to send a 2 and 3 to this function. So when we run this code, notice it works fine. But on the other hand, remember this use function would have been written separately. We come along later on. This is not that it's in the same class. This could be completely in a different class, and the use could be in a completely different library. Now I come along and I say, oh, look what I found. An efficient randomizer extends randomizer. So for all practical purposes, I should be able to send this all right. So what am I going to do? I send the efficient randomizer, and notice things go up in smoke. It failed at runtime even though the compiler didn't complain. And why didn't the compiler complain? Because the compiler designed by contract was not violated, and to the extent the compiler can see it. But at runtime, it recognizes that we are violating the expectation of the efficient randomizer, but we didn't break any contract of the randomizer. That's exactly what this says don't do. Derived class services should require no more, and our derived class required more. No, that's not allowed. Likewise, in this example, if I were to rewrite this, well, before that, so what should I do really if I want to make an efficient randomizer work in place of a randomizer? I need to redefine this. What I could do is, this is efficient if 2 is greater than or equal to 2 times from, otherwise it is only as efficient as, let's say, efficient as the base. And that's perfectly okay. So notice what I'll do in this case. In the next rand, what I will do then is I will say in this case, if, for example, from is less than, let's go through this condition. So if from is less than or equal to 0, and in fact this would be a lot better to do it a little differently. So let's go ahead and do this a little differently to refactor and make this work. So notice what I'm going to do in this case. The first thing I will do is I'll refactor this part. So I'm extracting that method as verify, let's say, a precondition. So I verified the precondition and I made this into a protected method. So now within the efficient randomizer, I'm going to first say verify precondition from comma 2. If you did not meet the precondition as set by the base class, I'm going to reject it. But if you meet the precondition, then I'm going to say if 2 is greater than or equal to 2 times from, then I'm going to say in here do efficient algorithm. And I can then say return, again let's fake the result here, let's say from plus 1. Else, so what do I do otherwise else? I'm going to simply say super dot, and I can say in this case next to random from comma 2. Now notice what I've done. I've not violated the precondition. I've only said I will comply with the precondition, but I will do things more efficiently if you're in compliance with the precondition. And if you're not really into the special area that I can give benefit, I'll fall back. So now if I go back and try this particular example again, notice that in this particular case, I get 2 and 2 as a result when there is no way to provide more efficiency. But on the other hand, if I did 4, you can see that the results are different. Obviously, it's random. And in this case, of course, we can say this is more efficient than the other one because it went through this route, and internally the algorithm could be more efficient. So the point really is, do not require more than the base service. Likewise, do not promise any less. So let's say for a minute, the base says, I'm going to return a random number, and it says the random result will be from is less than or equal to random result, which is less than or equal to 2. So it says the result is going to be in this range. From is less than or equal to result, which is less than or equal to 2. Well, that is the promise made by our randomizer. In the efficient randomizer, my algorithm is so efficient, but it says that the result is going to be from less than or equal to random result, let's say, which is less than or equal to, let's say this is going to say integer dot max value, let's say. Well, sorry, that is not acceptable. Why is it not acceptable? Because the promise is that you will give only in that range. Now we are violating that promise by saying, I'm going to be outside of that value. So this is a violation of the promise. You're promising less, while the base class said, I will guarantee the range. What does that mean then? If I said I want a random value between this range, I'm not suddenly going to go and check to see if your result is outside of this range because you promised. So as a user of this particular class, I'm not going to check for the result to be outside of the range because the contract says it'll be in the range. But now all of a sudden, when I substitute an efficient randomizer for randomizer, I'm left with the range outside, and that could cause havoc in the code because I'm now receiving a value I never expected, and I didn't do a checking because the contract said, why should I do a check unnecessarily? And that goes and causes other problems for me. But on the other hand, let's say this code says that I will return a result for you, but it says from is less than the result in this particular case, and then it says less than 2. So this efficient randomizer says the result I return will not include the from and to. That's okay because you are still in compliant. So your base says this is the range of data, and the result says my range of data is inside of that. We are okay. You didn't break the promise. The base promised this is the range, and the derived says I'm still within the range. But if your derived says my range is this and your base says my range is this, then you are breaking the promise. So again, whether you're breaking the promise or not is contextual. So you need to ask yourselves, am I really violating this? And we got to discuss about it. It's the interpretation of it, and that is why this is an advertised behavior as we infer from it. Now, I'm sure you understand this. In the social world, a company often could get sued for inappropriate or misleading advertisement. And usually an advertiser may say something and maybe people misinterpret totally different than what they really are providing. And so that is why it's advertised, not contractually written down. It is what you would expect of it. And that's what Liskov substitution principle says. Now, of course, we got a lot more to talk about LSP. We have merely scratched the surface to understand what the contract says, but I want to give you a little bit more and a few more examples actually. So we got quite a few things to talk about, and we will do that in the next part of this presentation.